Here we are again, next math notes, section 2.3.1, slope as a rate and dimensional analysis. Some of the stuff we just covered in the last math notes. So, slope of the line can represent many things. It depends totally on what you're graphing, okay? In the big race, you concentrated on situations where the rate of change of the line, i.e. the slope, represented the speed in meters per second. That would mean that you had a graph that had a y-axis in meters and an x-axis in seconds, so that when you had a line that went up, it went up by a certain number of meters over seconds, so your slope was in meters per second. However, the rate of change can represent many other things besides speed depending on the situation. Since the slope of delta y over delta x, the units of slope are always whatever the units of y are over the units of x. Often rates of change are written as unit rates, that is the rates with the denominator of 1. In the situation shown in the graph of the right, the slope is 21,000 people over 7 years. In other words, we have a y-intercept right here at 0, 10,000. So in year 0, there were 10,000 people in this town of Smallville. In year 7, there were 31,000 people in this town. That's a huge amount of growth. So the unit rate of change of the population is 3,000 people per year. So we take the delta y. The change in population over that time was the 21,000 over the delta x. The change in years was 7. 21,000 divided by 7 is 3,000, and our units were people per year. All right. For dimensional analysis, we touched on that a little bit in the last math note videos when I had you convert between, whatever it was, gallons per minute and liters per second, and then when we did conversion of speeds as well from miles per hour into feet per second. All that is part of dimensional analysis. When you're doing dimensional analysis, you're going to use different units for rates of change or any other measures. And along with the conversion factors from the last math notes. This says use the reciprocal of conversion factors as needed to make giant ones out of the units. In other words, to cancel out a top with the bottom, for example, as we did in the examples in the last math notes. So, for example, to calculate the rate of change of the population of Smallville in people per hour, follow the steps at the right. So we need to convert years into hours. They have one method here that shows everything. If you want to take a look at it, you can pause it. Right now, I'm going to go ahead and do my own version of it down here. And we're going to convert 3,000 people per year into people per hour. So I would start with 3,000 people per year. And we know that 1 year is 365 days. I put the year on top so that it would cancel with the year on the bottom. I know that 1 day is 24 hours. So now that day cancels with that day because we have a big 1 involved. And are we done? Trying to get it into people per hour. I think we are. People per hour. Yep. So let's see if we get the same method or the same answer. We should. On the top, we multiply across 3,000 times 1 times 1 gives us 3,000 people. On the bottom, 365 times 24. 365 times 24 gives us 8,760 hours. And then we say 3,000 divided by 8,760. And we get 0.342 people per hour, which hopefully, again, is the same thing that they got, which it is. Okay? So there you go. Slope, dimensional analysis. Main thing is, guys, always think about what your units are in the equation. You know, when you're writing an equation, the units matter. There's a difference between people per year and, you know, dollars per hour. Those are not the same thing, so we need to be aware of that and recognize it when we're creating our graphs. All right, guys.